Hello and welcome to this video on Foucault's pendulum for advanced experimenters. Why advanced experimenters? Well, I've been researching the pendulum since 2015 and a small workshop, and I've come across quite a bit of knowledge I'd like to pass on. It's quite advanced knowledge that challenges the current narrative, so it would be for anyone who wants to research with it, who's prepared to spend quite a bit of money. Not a novice or a school student who's just after a ball and a piece of string and a hook. This is not what we're looking at. Pendulum manufacturers, also flat earth experimenters and debunking the pendulum. I myself is 60 globe and 40% flat, and I'm heading more towards flat after those experiments I did on Galileo's ramp. There's certainly a lot of inconsistencies with the narrative, and it needs to be challenged more. Religious groups. Also, this affects me. I'm a Christian, and clearly in the Bible, Psalms 93 and 96, no doubt about it, says the earth is fixed and does not move. To me, I have a problem with this. I've asked many theologians, many priests, pastors, look, could you explain this to me? I have trouble with this. And I get almost a textbook response. It's from a cue card they read, and it's the same thing. We've been to space, man has been to space, we've looked at the earth, it spins. There's no doubt about it. The Bible speaks in metaphors, it speaks in symbolic language. We can't really, that's not what it's saying. Oh, okay, so I haven't been to space. How do I know that the people who have been to space are not telling me a lie? Well, we have to trust them, and it's basically, we know that that's true, that they have been to space. Everything means the earth, we've seen pictures of the earth spinning, there's no doubt about it. But then I say, well, did the Bible lie? Is that a lie? The earth is not fixed? Oh, then the argument breaks down a bit, and I have to leave it because it touches it's a touchy subject. Someone's lying. Okay, gyroscope manufacturers. Yeah. Wow. This could get expensive if we start getting to inertia gyroscopes, ring lasers, and we start talking about angular relativity. These are unchallenged waters, and I have gone into them quite a bit with this pendulum. So again, there's inconsistency. So get ready for this project will not be this will be expensive. I'd say $2,000 starting off to $5,000 will be intermediate point. That will you'll cut off there. You'll say this is not worth going any further. If we start getting and challenging ring lasers and angular relativity, the price will start climbing. This $5,000 thing will be, you'll be going, okay, it's easy for me to get in a plane now and go to Paris and see the real thing hanging in the museum in Paris. For $5,000, I'll see the real thing. But again, you won't be able to. You'll be looking at someone else's manufactured one. So to truly investigate this, you have to build each stage yourself, which I will guide you through, and we'll do small experiments to test every concept of the pendulum. So you'll do those experiments as well. You won't just trust my word for it. And give you an eye of a cost. This is something I come across. The aglet is the small brass component that will hold the cable, and it'll be your interface to the cable, allow you to secure the cable to the bob on the bearing surfaces. Now imagine this is the cable. It'll be an optical fibre cable. It'll be glass. It won't be any multi-core cable. It'll be a mono cable, and the aglet will be a brass aglet. Now you'll go to a manufacturer, a machine shop, and say, I would like a small aglet made up 5mm long by 3mm in diameter, and it has to have a optical fibre mounted hole with the same size as this optical fibre to mount a precise hole. There's no movement, and the machine shop will say, yeah, that's no problem, we can do that. Probably set up the lathe, probably $100 to set up the lathe. The brass is nothing, we won't even charge you. They probably wouldn't even charge you for the brass, but the setting up of the lathe. And then you say, oh, it's to mount a glass fibre, not a steel cable. And they go, oh, okay, all right. And it has to be very precise. It has to fit exactly. Oh, okay, yes, we can do that, yeah. And it's going to be preloaded in a jig, centre to centre. Oh, okay. Whoa. Oh. And I can show you how that'll be done. So if you need to go to the manufacturer, they won't get such a shock. And you can show them a bit of this video. Otherwise, you might get rejected. Typically, they'll say, look, we're a bit busy at the moment. So, who was Leon Foucault? Leon Foucault was a French inventor and scientist who lived between 1819 and 1868. As we know, he proved the Earth turned with his pendulum. He invented the gyroscope. He discovered eddy currents and did early measurements on the speed of light. Interestingly enough, after the pendulum, he discovered the gyroscope, and I was sort of following the same sort of pathway myself. I realised that perhaps the pendulum had some slight drawbacks, and it needed another device to confirm the Earth spun on its axis, and I think I was sort of heading towards some sort of gyroscope. And we'll talk about that later on in many videos down the track, but why we need to go to something other than the pendulum. In addition, the speed of light measurement too. I also come across that when we start talking about angular inertia. Linear inertia, no problem, the speed of light all works, but when you start talking about angular inertia, our current narrative on the speed of light sort of has a few hiccups, so we'll talk about that later as well. But anyway, the big one was 1851. Finally we finally proved that the Earth was spinning on its axis. Everyone guessed it was turning on its axis. So the experiment that Foucault set up in the, I believe it was the Louvre in 1851 in Paris, was bigger than the moon landing. From all accounts I've read, it was bigger than the moon landing. So that's how everyone had been just waiting to prove something that the Earth spun. After this 1851, around 1852, this hysteria broke out. Everyone was making pendulums, from backyard inventors to universities, and by all accounts there's something but hundreds, thousands to millions were made. So there was a lot of them were made, which is doesn't look good for the flat Earth, because if millions of these things are made, it doesn't look good if it's going to be hard to debunk. Everyone was making them and they're all coming up with the same answer. All right, right. Well, I think we've finished the video now on our introduction, and we'll just give you a brief. What we're going to talk about in the next video will be the decoupling, how the pendulum's decoupled, the bearings that are associated with decoupling the pendulum from the Earth. So otherwise, the Earth, as you know, the pendulum is fixed on a frame bolted to the Earth, so you think, oh, hey, what's going on here? This thing's bolted to the Earth that's supposed to measure the thing that's turning. So I'll just quickly show you my little experiment I've set up just to get the concept in your mind, and how we decouple the pendulum a bit. So just stand by for that, just only a few minutes. So here's my small demonstration experiment, which can It's not a precise experiment, but it is excellent for showing decoupling. You might notice here we have a bob, brass bob, our fibre optic cable, and our coupling bearing at the top here, which is magnetically coupled. The bob there's just enough magnetism to catch it. So we're on the threshold of the bob releasing. The magnet, the design of this point centres always in the centre of the magnet, and as in part 2 of the next video, we'll show exactly how this decoupling is done and why it's important to decouple as the Earth spins below the magnet, below the bob, and you'll see this decoupling effect. Alright, I think that's the end of the video, and thanks very much for watching, and we'll see you in part 2.